In this video, I'm going to introduce you to a smoothing filter. It's sometimes called the running mean filter or the mean smoothing filter. And this keyword mean here already tells you about the definition of this filter, how the filter works. So this running mean filter works by setting each data point in the filtered signal to be an average of the surrounding points from the original signal. So for example, this data point in the filtered signal might be the average of this data point and one data point previous and one data point post. Now, the number of data points that you go backwards in time and forwards in time is the key parameter of the mean smoothing filter, and that's called the order of the filter. Here you see the formula for this filter. Now, the formula looks more complicated than it really should be, given the straightforward concept. So essentially, you set each point in y, so each time point t in the filtered signal y, is defined as the sum of all the data points in the original signal x going t backwards in time k points and t forwards in time k points. So here you sum all of these up, and then you need to divide by the number of time points, which is 2k plus 1. There's the plus 1 here because you go k backwards and k forwards, so you end up with 1 in the middle. So this would be for this time point, and then the next time point would be this average 1 point before and 1 point after, or more general, k points before and k points after. Here is an example of what the smoothed version of this signal might look like. So the white line is x, that's the original signal, and the pink line here is y, that's the filtered signal. So you can see what is the effect of this mean smoothing filter. It's basically like taking away the sharp edges of the original signal. And the larger k is, the smoother this time series is going to be. Now you can already see here that there's something funny happening at the edges here. These are called edge effects, and in general, you always get something bizarre happening at the edges of your time series whenever you apply any kind of temporal filter. You will see these edge effects every time you apply a temporal filter to data, regardless of the type of filter. So then the question is, what do you do with these edge points? There are a few options. One is to set them to be the original signal, so the filtered signal, the pink signal, would go here, and then here it would stop here at this point. Another is to simply ignore them, so you would just crop off the first and the last data point from the filtered signal, which is what I'm showing here. Unfortunately, there's never a best or optimal way that always works for dealing with edge effects. So usually you'll have to figure out what's the best way to deal with edge effects on a case-by-case basis, given your specific application. Okay, so this is the theory of the running mean filter. Now let me show you how this looks in MATLAB. Here I'm creating a signal. These are the properties of the signal. So we have a 1000 Hertz sampling rate. We'll set time to be 3 seconds, or I guess technically it's one sample point over 3 seconds. And what I'm going to do to create this signal is interpolate across a couple of random time points. I'm going to use 15 random time points and then linearly interpolate across them. Let's already have a look at what this looks like. So I can say plot, and we have time, and then ample. So this would be the original signal, looks something like this. And then I'm going to add noise to that, and then you can see what that looks like. So here's our noisy signal. Okay, now here I'm initializing the filtered signal to be zeros. That means that there's going to be zeros coming up at the edges. So I'm using zeros for the edges of this filter. Here's where I implement the running mean filter in the time domain. You will see in the section of this course on convolution that it's also possible to implement this kind of filter in the frequency domain using spectral multiplication. That's thanks to something called the Convolution Theorem. You don't need to worry about that now. I will talk about that in the section on convolution. You can see that I'm looping from time point I to the end of the time series, almost the end of the time series. You can't start exactly on the first time point, and you can't go exactly to the end of the signal because you need to go from I minus k to I plus k. So, and here's basically the filter. So I set the filtered signal at this time point is the average of the signal from previous k points to plus k points. Now I've specified k here in terms of the number of points. However, time series data, people typically think about time in terms of milliseconds or seconds or minutes or whatever is the relevant time scale, but some meaningful time scale, not necessarily points. And that's why I convert from points from this arbitrary index number here into time in milliseconds. So this is the formula. Basically, this is saying the total number of points, so the total size of the window, times 1,000 and then divided by the sampling rate. And this will give you the window size in milliseconds. Now, in this particular case, it turns out that because I set the sampling rate to be 1,000, the window size is the same thing as, or the window size in points is the same thing as the window size in milliseconds. But that's generally not the case for sampling rates other than 1,000. All right, so that's essentially the mean filter. Let me now show you what this looks like. Here is the original signal in blue, so this is the pure signal plus the noise, and the filtered version in red. And what I'm highlighting here with this gray line is the size of the window. So this data point here at this dotted black line is the average of all of these surrounding points here. So there's a couple of interesting things that you can look at here. First, it's interesting to see that this isn't totally a perfectly smooth version of the signal. It's still a little bit rough. And if you wanted it smoother, you could increase k. So let's try k equals 40. And now it looks a little bit smoother, although it's still got some rough edges around here. Another thing you notice is these funny things happening at the edges. These are the edge effects. Now the way that I have set up this filter, it's initialized to 0. The output is initialized to zeros, and that's what creates this awkward jumps here at the beginning and at the end. So another possibility is instead of initializing this to be zeros, you can initialize this to be exactly the signal, so something like this. Now that doesn't give you this sudden drop down to 0, however, it still gives you a kind of bizarre looking filtered signal where there's a lot of really high frequency activity in the beginning and at the end. As I mentioned during the slides, there isn't really a whole lot that you can do about this. Edges are always going to look weird. So this is the running mean filter. It's a very useful filter, particularly when the noise is normally distributed. This is not an appropriate filter for all kinds of noise. This is really specific for when noise is distributed positive and negative relative to the signal of interest. I encourage you to continue exploring the mean filter in this code, and I will see you in the next video.